So good afternoon. My name is Olivier Steiger. I work for the energy company ABB and at the Corporate Research Center. I'm going to talk about the signal processing scheme for electro-optic voltage sensors. And first, I would like to spend a few words about what kind of sensors we are talking about. These sensors are actually used for very high voltage. So the typical rated voltage of such sensors are between 120 and 800 kilovolts, but you can also go above the megavolt depending on the physical design of your sensor. This is of course done a lot already nowadays. I mean, all energy distribution and transmission substations have these kind of sensors, but they are not optic nowadays. They are typically using voltage transformers. So these are really regular transformers that are integrated into some protected environment, typically filled with oil or possibly with SF6 gas. And with respect to that, we have some serious advantages from using an optical technology. First of all, the size and especially the weight are considerably reduced. So we are talking kilograms instead of tons, to take European measures. Then the bandwidth can be very high of such a voltage sensor. You can easily measure up to 100 kilohertz sampling rate, which is not possible with conventional transformers. There are special transformers, but they can then not be used for the normal measurements, and they are very expensive. The safety of operation can be improved because it's possible to make these sensors without oil or gas insulation, and this is a serious advantage in particular in terms of environmental compliance also. And as I've told, the rated voltages are the ones indicated here. Now, the principle of operation of these sensors is actually exactly the principle of operation of the bow sensor that we have heard in the previous presentation, but it's of course applied to a very different type of application. So we see this here. The main element is this VGO crystal. It's an electro-optic crystal. And to this crystal, we apply the full voltage to be measured. Actually, there are schemes where you apply partial voltage. You can split your voltage amongst several crystals, but here for simplicity, I illustrate it like that. You have a birefringence effect inside this crystal, which basically causes a differential phase shift between two light waves that propagate with orthogonal polarization. So we achieve this by using this polarizer here, which is placed at 45 degrees with respect to the main axis of the crystal. So you have basically, if you want one light beam propagating in the direction of X and one light beam propagation in the direction of Y due to this 45-degree angle. And between these two light beams, you will have a phase shift, which is due to this electro-optic effect in the crystal. And this phase shift is probed by a second polarizer, which is placed at the other end, and we see it here. Forget about the second channel for the moment. I will come back to that later. So this allows us to probe the phase shift between the two waves, which is proportional to the voltage, using a photodetector. Now, what does this signal look like? This is here, and again, we have two signals. I will spend a few words about this in a second, but now let's just consider the black signal here. This is the signal as a function of the applied voltage. So this unfortunately does not have a linear shape. It has a cosinusoidal square shape, and this of course leads to non-linearities of the sensor, but these are not a problem in the application that we have at hand here. The voltage here is called Vπ because this is just the voltage that generates a phase shift of P between the two light waves. And this voltage typically for a VGO crystal is of 72 kilovolts. So the consequence here is that when you have a voltage like the rated voltage of 300 or 500 kilovolt, then you are going through several periods of this response. And this, of course, is bothering us because we don't know a priori where we are. So the detector signal is ambiguous with respect to the period. It's what we see here. It's also ambiguous with respect to the sign because, of course, what you get out, the intensity signal, is here on the y-axis, and to reconstruct the applied voltage, you need to take an arc cosine, and this has an ambiguity on its sign, so you don't know if it's plus or minus. To solve these ambiguities, especially the sign ambiguity, we add a second signal, and we have seen this on the previous slide. This is the second channel, which is delayed by a quarter wavelength using a quarter wavelength plate. And this is this dotted signal here in the graph, and this will allow us to reconstruct the sign. So now let me tell you about what we do exactly. The task of the signal processing is to resolve these ambiguities and of course to retrieve the correct value of the applied voltage with a high precision, as we will see in the results. And the particular features, because of course we are not the first doing that, obviously, but the particular features of our signal processing scheme is that it extracts also the sensor temperature from the signal itself. So far this has been done using temperature sensors. We extract it from the signal. I will tell in a second how we do that. And this is actually needed because if you want to reach metering accuracy, which is an accuracy of 0.2% of the rated voltage, then you need to do temperature compensation because you have a variation of this VP voltage that I have been shown before, which is bigger than the 0.2%. So you need to compensate there. Also, we extract intrinsic phase shift because the VGO crystal does not necessarily lead to a waveform that looks as nice as this one. This peak here could be at some volt instead of 0 volt. And this needs to be taken into account as well. So what does the signal processing do? A bit in a nutshell here, but if there are questions about this, I have some additional slides, so I could go into more details. The basic scheme is very intuitive. You compute the arc cosine of the signal that you get out. Then, and this is state of the art, this is not new, then you use this second signal here to get the sign, because as you can see, for instance, if you have this point or this point and you are not sure which one corresponds to the voltage that is currently applied, then by referring to the second signal, you will get very different output, because here you would get this 0 output basically, and here you would get this maximum output. And by looking at that signal, you will know which of these 2 points you have. And then to know on which period you are, what you do is you actually count the number of zero crossings that you have been going through, because you apply an AC voltage with these kind of sensors, which means that you are really going through the voltage range that we have here on the x-axis. And therefore you are also going through the zero crossings of this normalized signal. And by just counting this, you will be able to know where you are on your signal. So all of this is relatively old and has been patented by other people than us. The new contribution is this one. It's this determination of the phase shift and temperature compensation, which makes a big difference in terms of applicability, because you always have this temperature dependence and you always have a significant intrinsic phase shift of the crystal. So what do we do here? I explained it for the temperature, and then it will be basically the same for the phase shift. What we use for the temperature is the temperature dependence of the quarter wave plates that I have been talking about before. So this is basically the same thing as the scheme that I've shown before, just another visualization. Here we have the two output channels, and on one of the channels we have the lambda force plate. And this has a temperature dependence that is quite strong. That's not the one we want to compensate for, but that's the one that we use now in order to get our actual temperature. What does this mean? We here see, first of all, in blue, the conventional ideal signal that we would have. It's here normalized between what I call I0 and 0. And as we can see, we have a 0 output at 0 volts. So this is an ideal signal. Now, if our lambda quarter plate leads to some phase shift, then we have this red dotted curve, which of course is non-ideal and which does not go through 0 at 0 volt, but somewhere else. And we can observe that the effect of this is exactly the same as the effect that we would have if instead of applying perfect AC voltage without any offset to the blue curve, instead of applying that, we would apply an AC voltage with a DC offset. So this observation can be used because in actual applications, in substations or in the grid, in the power grid, you don't have a DC offset, or at least you don't have it for long. It could happen in some transient conditions that you want to measure, but in the mean, the DC component is 0. Therefore, if in your reconstructed signal, in the voltage that you reconstruct according to what I said before, you observe a DC offset, then you know that this full DC offset will be due to the quarter wave plate. And that's all you do. You then retranslate this, the formula is in the paper, of course, you retranslate this observed phase shift from volt into radian, and then you know the effect that your quarter wave plate had, and therefore you know the temperature, because you have characterized the temperature dependence of your quarter wave plate. That's all there is to it. And you do exactly the same thing, but on the other signal that does not have the quarter wave plate, in order to know the intrinsic phase shift. And then you have these two parameters. You can compensate for them in your final reconstruction, and you get a high precision reconstruction of the voltage. Of course, we have verified this. This is the setup that we have used to verify it. So here we have a prototype of our actual voltage sensor. The BGO crystal would be a very small thing here in the middle. So the BGO crystal only has a length of 30 centimeter. The whole device here is 2 meters more or less in height. And we apply the rated voltage to this device. It has some insulation, of course. And then we have here a light source. We inject it. It's actually a mirrored configuration. So instead of going through with the light, we go to the mirror that is on top of the BGO, and we come back and go into our two detectors. This first is a reconstruction in the time domain. So what we see on top are the time signals generated by the two channels. That's what they look like. I won't go into the detail. And this is the reconstructed voltage. Here it's just shifted for representation purposes, but actually this would be perfectly superimposed. And here is the error as a function of the samples, so really over these periods. And we can see that the error of each sample is quite low. It is typically below 1%. More interestingly, of course, is what we get in average, because that's what you need in order to fulfill your standards. So there are two very important standards in practice. One is the metering standard, and one is the protection standard. The first one you use to bill the electricity to your customers, and the second one you use to switch off some electrical lines when you have a problem on them. And for metering, we need an accuracy of 0.2%, and for protection of 3%. And what we can see here is that both standards are met with our prototype and will be met also with the corresponding product. So basically, we have proposed a signal processing method that is not revolutionary, but it's new because it makes a big change with respect to the state of the art, as you have now the intrinsic phase shift and the temperature. And with this, we are able, both in theory and in practice in lab tests, to provide accurate measurements that fulfill the IEC standards for metering and protection. And that's it from my part.